let's do a demo. So what I've got at the front of the room to show this, I'll show you the picture and then I'll move the screen over for the screen over for the people in the class in a moment. I've got the picture in the room. I've got a bar. I don't know. I think it's about 60 centimeters long, roughly. Not quite. Well, that'd be about, yeah, it's about 60. 30 would be about that. It's about 2 feet. It's about roughly 60, maybe 58, 60 centimeters long. It's about 7 centimeters wide and about maybe half a centimeter thick. It's made of aluminum. I have to get the exact dimensions and the exact alloy for us to be able to do a calculation with it. What I'm doing is I'm driving it at one end. So on the picture, what I've got here, and it's a slightly different setup right here than I have in the picture, but this little device right there is just a coil of wire. So it's a coil. It's just a holder for the coil, but I've got a coil of wire, and underneath that coil, I'm going to have a magnet. In this case, I have it's a neodymium iron boron magnet, so super strong but super tiny, and I have it attached with wax to this bar. And if I put a coil on top of the magnet and put a current in the coil, but it's an alternating current in the coil produces a magnetic field, and that's going to push and pull on the magnet, but it's not going to be in contact with the bar, so I can drive the magnet, make it oscillate, but without having to touch it. And then at the other end, down here, I've got an accelerometer. So right there is an accelerometer. My pen will write. It's going to measure the response of the bar. And I've got a couple of other devices that we'll look at right now, but what I'm going to do is I'm taking this this is a 1997 vintage frequency analyzer. There are a couple things that it's an old device, and you don't see a whole lot of these in industry anymore. We tend to use data acquisition boards and MATLAB and software to do things. There are some things that this will do circles around MATLAB and software and data acquisition systems, though. And there are some things from a teaching viewpoint that I really like. It actually has 2 FFT chips inside that will allow me to take 2 channels of data, and I can look at them independently of each other with completely different resolutions, completely different sampling rates. So there are some pretty cool things that I can do that way. I can do order tracking. I can do order tracking, I can do octave band or third octave band or 12th octave band analysis. I can do swept sign measurements. I can do histogram tracking. I can do frequency response and all kinds of, so there's a lot of cool things I can do with it. I still use it for a good amount of my research. Let's hit a button so that it gives a thing, and let's clear off the screen. So what I'm going to do is I'm going to use this thing as a source output, and I'm going to use the source output. I've got that connected with a wire to the coil. So I'm going to send a single frequency signal to the coil, pushing and pulling on the coil. Okay? So let me, I'll show you the data on the page after. Let me move this over so you guys can see what I'm doing with the picture. Christine, if you want to go ahead and pop that screen in, and then pop the inset. There we go, so we can see the screen. So what I'm going to do is I'm going to send a signal to the coil. That's going to drive the bar, and then I'm going to measure the response of the bar, and I'm going to use what's called a swept sign measurement. And a swept sign measurement sends out a signal, allows the signal to settle for a certain length of time, measures that single frequency response for a certain amount of time, then changes the frequency, lets it settle, measures the response at that frequency, changes the frequency, measure response, and I can do a sweep through the whole data. So I'm not, I think I have everything set up when I pulled up my setup file. So if I hit start, might take a second or two to run through, but we'll be able to see if it's collecting some data. So there's a peak. And then there's a second peak. I'm not sure if you can see as it coming in, you might be able to see it bounce a little bit, like it's going up and then comes down and bounces a little bit. So 1, 2, 3, 4. Unfortunately, the camera just can't get in and zoom on that. I'll give you the frequencies. We'll find the frequencies and write those down in just a minute. So 1, 2, 3, 4, 5. Now, from what you can see, would those be integer related or not? You're shaking your head, Trudy. Why would you say they're not integer related? Hit the microphone there just so you can answer it, so the people at home can hear you. Okay, but I can't see dispersion here because this is a frequency spectrum, not time. If they were integer multiples, what would you expect the spacing of all the peaks to be? Equal. But these are not equally spaced. If there's an integer multiple, 1, 2, 3, 4, 5, on a scale of linear frequency, I should have told you it was a linear frequency scale, they should be equally spaced, all those peaks, but these are not. The first ones are closer together, and then they get farther and farther and farther apart. Okay? Now, what I was mentioning for a second, the fact that as this signal comes up, it went up and then it bounced a little bit, and it came down and went up and it bounced a little bit. If you go back to page 20 of your notes, I'll pull it up for just a second. If you go back to, you can leave the cameras right there, Christina. If you go back to page 20 of your notes, we were saying that if I had a system that has a really high Q, and I sweep through the frequencies, if I don't go slow enough, I can miss the resonance. It'll hit resonance, and I'm changing the frequency, and it's still trying to oscillate at its very low damping, high amplitude value, and I've changed the frequency, and so it has a bit of a beat. And so I get this up and down, this ring down afterwards, which is what I was actually seeing when I went through. So in order for me to slow that down, it just takes way too long for the demonstration, so we're going to live with it and just see what it is. But that's there. It is a real problem with any system that has a very small amount of damping, a high Q value. When you're trying to sweep through the frequencies, you got to go really slow, otherwise you'll miss the actual frequency and the amplitude if we're looking for it. Just wanted to highlight that because it's kind of a cool to see that. All right, let's bring this back so you guys can see that again. Okay, so somewhere off to the, actually what we're going to do is, what I have right now corresponds to the blue. Move that up to the top of the page and I can move this down. This corresponds to the blue curve. And I'm not going to tell you what they are yet. Well, we're driving the bar in Flexural, so let me just do that. I do know that these are the flexural bending. These are the flexural bending modes. You can keep it inset like that. You can move the other camera around, but keep that one inset since we have it there. But let me go over here to the analyzer and find out what these values are. So if I'm going to move my cursor around to try and see the values, this first one is at, where'd it go? 82 hertz. It's a little bit lower than I thought. 82 hertz, and the next one is 248. So if I put some numbers on this, 82. The next one is 248 hertz. The next blue one is 482. I can't see. 796. 482 and 796. So 482 and 796. And if you just want completeness, the last two, I've got a 1185. 1641. 1185 and 1641. So if, I don't know if anybody got a calculator on your phone. Tony, you got a calculator there. If you got a calculator, take 248 divided by 82. And Shruti, if you would take, so 248 divided by 82. And then Shruti, if you would take 5 squared divided by 3 squared. 3.024, 2.77. So I think this is not quite where I want it to be. That first one I really missed on the frequency because I think of my sweep. So I tell you what, in order to make this work well, I'm going to, because that frequency should be about 90 is where it actually is for this bar. So if you change the 82, I'm just going to lie to it right now. So because I know that's where this, the 248 is pretty close to being correct, but if you change it to a 90, then how does that change your 248 divided by 90?
That's 2.7555.
2.7555 is a lot closer. 2.76 is a lot closer to the ratio of the second bending vibration to the first bending vibration. The reason we missed 90 is because I was sweeping up too fast, and so we're on the low side of the frequency because it's trying to get there, and I missed because it bounced because of that, the effect on page 20 with the ring down and the fact that I'm sweeping too fast with a very high Q oscillator. If you took 482 divided by 90, that should be the same as 7 squared divided by 3 squared. So 482 divided by 90. What do you got?
482 over 90 is 5.355.
5.355.
And then 7 squared over 3 squared is 5.44.
5.44, so pretty close. Again, we're slightly, when I did this in my lab for the data, I had to go a little bit slower than I'm doing right now just so I could actually see the data. I don't want to take 5 minutes for a single sweep right now, so we're seeing the difference. But we're getting something that looks like it should. The ratio of second frequency to first frequency should be about 2.7. We're getting about 2.7. The ratio of the third frequency to the first frequency should be about 5.4-ish, and we're seeing about 5.4-ish. Okay? Now, right now, the only ones I'm seeing are the bending vibrations because I happen to have the accelerometer in the middle of the bar, and I'm driving it in the middle of the bar. Okay? So I'm driving it into vibration. If I was to take and move the accelerometer, so let's move it over to a corner and try to drive it. So I'm measuring it at the corner now, and I'm driving it in the center. Would you expect me to be able to see torsional modes? I'm getting some head nods. Let's try it. Let's see if anything is different. I move the accelerometer to the corner, so I should be able to pick up if the corner is doing something, and I'm driving it in the same place in the center, and we'll see if it does. I should have left the background picture up there, but we'll see if we get any other curves compared to what we had before. I've got 1, 2, 3, 4. It looks like I have the same things. I'm still getting some ring down because I'm missing. So I'm not seeing anything different. But I'm still driving it right in the middle of the bar. Yeah. So when we're measuring something, if I'm trying to see all the shapes that are possible, I got to make sure that I don't have the driver and both the receiver at a node. Torsional mode should have a node right down the center of the bar where the thing is twisting. And if I'm driving it at a node, the bar says, you can push however hard you want. I'm not vibrating at that location. So it doesn't matter where I put the accelerometer. I'm not going to see anything happen because I'm driving it at a node. If I was driving it on the outside corner and measuring it at a node, I would see nothing because the bar says, I'm not vibrating here, and the accelerometer says, I'm not measuring anything because you're not vibrating. So in order to see this, in order to see torsional modes, I got to reconfigure the system a little bit. Let's move the magnet over to a corner so I can drive it at a corner and measure it at a corner. I think I can make this work. Back it up just a bit. All right. So now let's hit start and see if I get anything. Now what I should see is this red curve. I should see something. All the blue peaks are going to show up because I'm still looking at the flexural bending vibrations, but I should also start up to see, so I got 2 peaks there. I should also start to see some torsional twisting ones as well. And we can see what those look. We'll get those frequencies and see what those are in just a sec. So each of these peaks now is showing 2 of them that weren't there before because now I don't have the accelerometer at a dead spot, at a node. So if you're ever making a measurement on something and you're trying to figure out why you can't see things, then move the accelerometer and or the driver and make sure that you're not driving it or measuring it at a node location, because if you're trying to drive it at a point that doesn't move, nothing's going to happen. If you're trying to measure it at a point that doesn't move, nothing's going to happen. All right, so red curve. See what I've got for frequencies. This first one down here, there's the 480 thing, 482. The 432 is our first red torsional. These are the torsional ones. What did I say, 430? 432, I just read it and couldn't remember. 432. 432 hertz is the first one. Any ballpark ideas where the next one should be? 8 something. 432. Torsional modes are integer multiples, right? So we should be roughly twice 432, so about 864 if we can do my math right. Okay, so I'm getting 867 right here, which is pretty close. I don't know what the frequency resolution is. It's probably a plus or minus 1 or 2 hertz on my resolution that I have the system at right now. And we still have the fact that I'm sweeping pretty fast, so I'm still going to miss a little bit, not be quite right on. Okay, so 432 times 2 is 860 something. Times 3 should be about 1300 somewhere. So let's see, the third one is about 13, 15. So 13, 15. And then the fourth one should be probably around 16, 17. Right up there at 1796. So if I take 867 divided by 432, that's going to be pretty close to 2. Because torsional modes are going to be integer multiples. And if I took 1315 divided by 432, I should get something pretty close to 3. What'd you get? It's going to be a little bit more than 3, I think, but it's pretty close. 3.0, that's pretty close. 4% error? Yeah, that's pretty close. I'd go for that. Government work. All right. 1796 divided by 432. 4.16, so not bad, considering that I'm sweeping pretty fast, and I'm also mass loading the structure just a little bit, and I'm warping it only on one side, so not bad from what I would expect to see. All right, let's do another thing, though. So let's see, Christina, you can take that picture out and zoom in on the table. And let's see, what I'm going to try to do is we're going to try to map out what's going on here. So I got to hook up a couple things differently. I need to take this and make sure that the amplitude is turned down and connect that here. So I'm going to drive the bar at a single frequency. And then I'm going to measure the near field vibration of the bar using a microphone. And I'll try to do this so that you guys can see what's going on. So what I've got in this microphone, I'm looking at the signal. I'm doing two things. I'm sending out I'm going to start out with 90 because that's where our first bending vibration should be. I'm going to send out a signal to the coil. That's going to make the bar vibrate. And if I turn it up just a little bit, if everything is working, I can feel the bar vibrating. You may even be able to hear it in the room. Okay. I'm sending that signal to an oscilloscope, and I'm going to send the microphone signal to the oscilloscope, and I'm going to use an XY trace, which allows me to plot one sine wave as a function of the other sine wave. If they're both moving, so they're both going to be recording the same frequency. And if they're both moving at the same frequency at the same time in phase, then I'm going to get, if they both start here and then they both go up, I would get a positive slope. That if they're both in phase together, I'd see a positive slope from this picture. Boy, I can't know if I can do this. Okay, so if one of them is positive and they're out of phase with each other, then I'm going to get a negative slope. So if I take a look at this signal, and I put maybe I'll crouch down on the floor here so I can see what's going on with it. If I put the microphone near, I might have to adjust the amplitude. I'm getting some buzzing. Let's move that so it gets a good clean signal. There we go. Let's see, can I improve that at all? That's about as good as I can go. If I touch it, I get a big signal. Let's turn it up just a little bit. I want to burn my coil out, but all right. So right now I've got a positive slope. If this is a pure bending vibration, maybe I'll change just the frequency just a little bit too. It's going a bit nonlinear. I'm pushing it a little bit hard. All right. There's a pretty good slope. Okay, if I put the microphone across the bar, across the width, the slope doesn't change. If I stay in the bar and go across the bar, the slope is still positive, right? Because there's no difference across the bar. But if I go down to one end, so down there it's a positive slope, and I'm sorry, that's a negative slope, isn't it? That would be a negative slope. And if I cross a node, there's nothing, and I'm now in a place that's a positive slope, and then I cross and get to another negative slope. So I can map out what this picture looks like. There's a spot right about, I think we did the math, or I showed you the results, about 0.22, 22% of the length. And then about 77% of the length are the places where it's nodes. phase at the end and the end should be the same, and the phase in the middle should be opposite if this is the first bending mode. So if I was to map out a picture, if this is the first bending at 90 hertz, then I should have a node, and I should have negative, positive, negative for that picture. Okay? If I went to the second bending pattern, which we said was, so what, 240, where's my picture here, 248. So 248 hertz. So let's change the frequency to 248. I'm getting some buzzing. I think I've got the coil hitting the edge of the... All right, so let's see if I can measure. I can feel it vibrating. I have enough of a signal I can see a slope. Positive. Let's see, I'm in the middle of the bar, right? Middle of the bar should be 0. Positive. Let's start at one end. I'm starting at the coil end, and it's positive slope, negative slope, positive slope, and negative slope. So negative, positive, negative, positive, but if I picked a place where there's a good slope and I go across the bar, I don't get any change. So this one at 248 would be a node right at the middle, and a node somewhere down here, and a node somewhere down here, and if I said, I don't remember what I said, positive, negative, would be what we see. Let's see, the next one was 432. So 432. Let's go to 432. I don't think it's getting too hot yet. I can smell something burning, but that's cool. It's not a good experiment if you don't make something smoke and blow up, right? Okay, 432 is the neighborhood I'm looking for. Let's see if I can see a signal. All right. Definitely seeing there. So I'm at the coil end. I've got positive. And if I go across the bar, I can't get there because I've got a screw in the way. On the other side of the bar, the other corner of the bar, it's negative. So positive on one side, negative on the other side. Christina, why don't you jump to the other, okay, the side camera. There, oops, yeah. Sorry, then you can see my hand going. So if I'm at this side of the bar versus that, there you go. It's really hard moving your hands when you're looking at a camera too. All right, so positive slope on this side, negative slope on that side. And if I go down the middle, there's the node right about the middle, and it should be negative there and positive on that side. So that's the torsional mode. So this one, there is a node right down the middle, and then a node right down there, and you got positive, positive, negative, and negative. And we could keep out mapping out the next several. Okay, I actually use this quite often. It's a handy trick that I learned in grad school, that if you're trying to map out mode shapes, you can use a small magnet and a coil to drive the system, and use a microphone and just use the Lissajous pattern on the oscilloscope and just look at positive slope, and you can see when the slope changes, you know, and you've got a mode shape. So if you're trying to find a structure, trying to find out where to put an accelerometer so that you could do a complete vibration test of a complicated structure, and I don't know, it's not a simple rectangle, so I don't know where the nodes might be, I could scan through and find some resonances, map it out with a microphone to get an idea of where the nodes and the antinodes are, so I don't want to put an accelerometer at a node, put it at an antinode. So that becomes a kind of useful thing. All right, I'm starting to smell some rubber, so let's turn that down. All right, you can put that camera shot away because I'm done with that part of it now. All right, that's kind of it's a neat experiment. It's a very simple tool that allows you to make some measurements and see something. So here's some more